So I think we're all probably quite familiar with ECDSA signatures. They're quite ubiquitous, right? Not just in an Ethereum context, but also in a crypto context. But I feel like there are better options out there now, and we've just kind of been reusing ECDSAs as just like this off-the-shelf kind of thing that we've just been using out of habit, right? They're easy to work with. Everyone knows how to work with them. There's standardized libraries for them. But I want to talk to you a little bit about Schnorr signatures, which I think offer a quite compelling value from a variety of different angles. So the first, smaller signature sizes. An ECDSA signature is 65 bytes, right? Which means we're going to be using 3 words, right, to store one of these signatures. But a Schnorr signature can be as little as 52 bytes, right? So you can save like an entire word of call data per signature. So that's out of the box, right? You already get some savings there. Now, I think one of the more important properties, though, is this property of malleability. So Schnorr signatures are non-malleable, provably non-malleable. Versus in ECDSA, you have some, you don't have this property, right? So what does that mean, right? Well, it means that signatures are not unique, right? You could have the same signature generated by a different combination of a key and a message, right? Another, permutation, right, is you could have a different signature, right, for the same kind of message, right? And so these are not, these are properties, right, that kind of reduce the level of security that ECDSA provides. Now, some of these, especially the second one, are more of a theoretical concern than a practical concern. What the second kind of form of malleability is really talking about is you can generate a triplet, right? That is a key, a message, and a valid signature, right? Without knowing, the private key of a key, right? So as long as you have one valid signature, you can just, of one valid triplet, you can derive other valid triplets from it. Now, deriving a specific triplet, right, would be like, stumbling upon, the key for the 0 address in Ethereum, right? So from a practical concern, it's not that bad, but from a theoretical concern, right, there is like a ton of leakage here in terms of data, right? To kind of condense this, right, I think the main takeaway here is that like signatures are not unique, right? You can't, have an identity based off of a signature. Versus with Schnorr, signatures are unique, and you absolutely can. So let's talk about something that ECDSA can't do: signature aggregation. So I think in the Ethereum community, we've kind of leaned towards BLS as being, the signature aggregation scheme of choice. I personally think that's a mistake. I think Schnorr signatures are much better in this regard. So, but let's just talk about aggregating signatures generally over ECDSA, and then we can kind of talk about, between different signature aggregation schemes like BLS and Schnorr, right? What are the differences there? So, if you're going to have multiple ECDSA signatures, right, you're going to have linear growth, right, not just in terms of like the data that you're, sending or storing, but also in terms of verification, right? So if you want 10 different people to sign something, great, you're going to have 10 different signatures, and you're going to verify, EC recover 10 different signatures. Well, what you get with Schnorr is that, well, one, you get this one signature, right? So you have this many-to-one relationship of signers to signatures, and so you get this really nice property of like constant size call data. for, right, any number of signatures. And the other cool property, right, is that you can do batch verification. You can do this in constant time, right? So it doesn't matter if you have 5 signers, 100 signers, 10,000 signers, right? Depending on how you set it up, verification of a Schnorr signature can be done in constant time. And so now, taking, reflecting on kind of Schnorr versus BLS, BLS is actually much more expensive to verify on chain. So I think people are really kind of sleeping on the potential of Schnorr signatures here. So even on the privacy front, and I will admit that this is a little bit of a reach, but one nice property that you get from Schnorr signatures is that you can't tell just from looking at the signature how many people have signed this signature, right? So with ECDSAs, right, 10 signers, great, you have 10 signatures, 10 different people signed this, right? But with Schnorr signatures, you don't have this property, right? So this can be useful in certain types of applications. And then, and I think this one is quite important. So let's talk about security. So ECDSA signatures are not provably secure. They are reasonably secure in a practical sense, but Schnorr signatures are different. Schnorr signatures have been proven to be secure. So using fiat Schmier, you can actually prove that Schnorr signatures are secure, right? So I think that's a very big reason to use them, right? So you don't have any surprises down the road, right? And so one of the key properties, right, and this kind of goes back to the malleability, right, and being provably secure, right, is that you have these strong guarantees, right, that these signatures cannot be forged, right? With ECDSA, right, if you have one valid signature, right, you can just change, let's say, the message, right, and do an EC recover, and it will spit out, right, some random signer, right, signed this. Well, some random signer didn't sign this, right? You didn't have the private key, but you were able to create this valid tuple, right? With Schnorr signatures, you can't do that. You cannot forge a signature without having the private key of a signer. Now, in terms of elliptic curves, Schnorr uses the exact same elliptic curve as ECDSA. So the same curve that's already implemented in Ethereum and in Bitcoin, right? You're not going on some unproven, underutilized curve, experimental. No, this is a battle-tested elliptic curve. So this kind of makes the comparison between ECDSA and Schnorr quite valid. And kind of from a production point of view, right, how has Schnorr been utilized? Is it safe? Has it secured billions of dollars? Yes, it absolutely has. Since 2021, Schnorr has been part of the Bitcoin protocol as part of their kind of signature aggregation scheme. And the arguments at the time were primarily, right, for security. So that's kind of I think one of the big takeaways here is that, Schnorr has all of these nice properties that make it really useful, but the main takeaway should be, that Schnorr signatures are actually more secure than ECDSA. So, how do you get started, right? I want you to go away from here and actually use this stuff and not just be that's cool. So at Chronicle, we've kind of created a library. It's very well documented. It's been audited by some of the major firms, and it's under MIT license. So you can go to our GitHub repo, type in scribe, and there will be a library, right, for Schnorr signatures. So definitely check that out. It's actually quite efficient in terms of gas. I think you'll be quite surprised. So, kind of let's talk about a little bit more of a production use case in prod. You know, why am I here talking about Schnorr? Like, why am I trying to make the case for this? Well, at Chronicle, we are an Oracle protocol. We spun out of MakerDAO late last year, and we've been using Schnorr signatures to great effect. Before, right, we had an Oracle scheme, right, where there were about 22 to 25 different, signers, validators, node operators, if you will, right, that were all, generating one signature each, and our Oracle would be, verifying each of these signatures. And, on a chain like Ethereum mainnet, that's quite expensive. There's a lot of computation involved, right, in verifying all of these signatures. And in an L2 context, right, it's very expensive, right, because if you have n validators generating n signatures, L2 transactions are essentially call data constrained, right, because all the data needs to be posted to L1, right? So the more data that you're trying to push to an L2 transaction, right, the more expensive the transaction is going to be. And so Schnorr kind of helps on all of these fronts, right? So one, we get constant time verification for compute constrained environments like Ethereum mainnet. And on layer 2, right, we get call data compression, right, because we don't need to have, 25 different signatures now. We can just have one Schnorr signature. And just to give you an idea of how effective this has been, I have here a table of all of the different kind of players in the Oracle space, and more or less, what they're using for gas for a certain number of signers. Now the caveat here is that not all Oracle protocols work the same. So some will go based off validators, some will go based off of number of data points, or some will do some kind of hybrid and call them first-party data providers. But from a technical point of view, it's all the same, right? The number of signers is effectively a sign of your security and of your decentralization, right? So if you can have a larger signer set, right, you can be more decentralized, but also be more secure, because the coordination effort, right, to manipulate the Oracle through a consensus, right, is much more difficult. And so with Schnorr signatures, not only were we able to achieve, orders of magnitude more signers or data points, right, than all of these existing solutions, but we were also able to get the gas down to anything cheaper than existing solutions, right? And at this 52,000 gas marker, I mean, of that 52,000 gas, 21,000 gas is the default Ethereum gas cost, right? So we're really converging on the limit here. And so we've actually, by leveraging multi-call, right, you're able to kind of amortize that 21,000 gas across, multiple Oracle updates that you can do atomically in a batch. So, with 2 Oracle updates, you can get it down to 47,000 gas, with 3 to 43,000, right, and eventually at the limit, you should converge to, 52,000 gas minus 21,000 gas if you have enough oracles that you're updating at the same time. So Schnorr signatures, really, really cool, really, really useful. Highly suggest everyone checks them out. So thank you very much. If you're interested in Chronicle, please follow us on Twitter at Chronicle Labs. And if you just want to chat about oracles, I'll be around here for a little bit. So thank you.